Hello, my name is Edresson Casanova, and today I'm going to talk about our efforts to identify COVID-19 using speech and copy in the Computational Paralinguistic Challenge. The INTERSPEECH Computational Paralinguistic Challenge 2021 proposed two computations related to detecting COVID-19 from audio samples. The COVID-19 speech sub-challenge offers speech samples, and the COVID-19 cough sub-challenge provides cough samples. We explored four architectures based on convolutional neural networks for the two sub-challenges. To address the scarcity of data in both challenges, we explored the transfer learning from large-scale pre-trained neural networks and the use of three different data augmentation techniques. We explored transfer learning from the models CNN14, HesNet38, and the mobile network version 1. Our models have been trained with our set dataset. Additionally, we explore the spec augment, additive noise, and mix-up data augmentation techniques. The data augmentation as performed in each train step, thus in each train epoch, the same sample as increased in a different way. Each model was trained using three different configurations. Simple handout uses the official train, dev, and test subsets, and use the entire sample content as input to the model. Windowed handout similar to simple handout, but the models are trained with a fixed size of windows of the input sample. K-fold cross-validation divides the train and development set into 5 folds. The evaluation is performed with an ensemble of all 5 folds. In our configuration, we train the models with 5 different seeds and create an ensemble for the evaluation. For COVID-19 speech sub-challenge, despite your models having a superior result in the development set, your models achieved a result inferior to the baseline in the test set. On the other hand, for the COVID-19 cough sub-challenge, your best experiments achieve a result 2% above the baseline. Therefore, your best cough model surpassed the baseline, and we had good results for the speech experiment, but it didn't surpass the baseline. So, continuing the explanation, in addition to the CNN14, HesNet38, and MobileNet version 1 models, we explored the SpiroNet model. SpiroNet is a convolutional model that was designed to detecting respiratory insufficiency in COVID-19 speech samples. This model achieved promising results in a scenario with high environmental noise. Following the original work, we trained the SpiroNet using mel frequency capture coefficients. On the other hand, the other models were trained using log-mel spectrograms. On the SpiroNet paper, we showed that the use of audio duration pad can facilitate the model's overfitting. Audio tends to be longer for advanced COVID-19 cases due to the respiratory insufficiency. Inspired by this, we propose to use the windowed handout approach. For COVID-19 speech sub-challenge, we randomly selected 3-second windows of each audio in each train step. On the other hand, for COVID-19 cough sub-challenge, we use a 2-second window. These values were chosen based on minimum duration of the samples from each dataset. Inspired by the ComPa 2020 Master Sub-Challenge winner, we use a K-fold cross-validation. K-fold cross-validation has the advantage to allowing the model to see all data in different folds. For the evaluation, we averaged the activations of the models of all folds. Although windowed handout looks promising because it artificially increases the number of samples in the dataset and makes everything difficult, in our experiment, the approach showed the worst performance of the 3 explored approaches. We believe the main cause is the selected window size. In the SpiroNet paper, we use a 4-second windows. Here we use 3 and 2-second window depending on the dataset. This decrease in input size can make the model learning more difficult. The K-fold cross-validation, despite showing promising results, also it didn't achieve superior results to the use of a simple handout. We believe that as in the separation of the fivefold, we didn't have access to speaker identities or language. Thus, the development and trained sets can share the same speakers, facilitating the model's overfitting. We also create two ensembles. The first was composed of the best models of which of the three approaches, and the second was composed of all your models. However, both ensembles didn't achieve the best results of the simplest handout approach on both sub-challenges. Therefore, your best model in both challenges used the simplest handout approach, which used the entire audio samples as the model input. Your best model in COVID-19 speech sub-challenge as the ResNet 38 model, which achieved 70.3% UAR in the test set. On the other hand, your best model in COVID-19 cough sub-challenge as the CNN 14, achieving a UAR of 75.9% in the test set. The code used to perform our experiments is open source, and thank you very much for your attention.
Okay.
Okay, thank you. Regarding data augmentation, do you think there's a risk that it could alter specific biomarkers of COVID-19 in speech coughs?
Yes, I think so. I think this can be a problem. First, for example, we append noise in the audio, so we append many things. So yeah, it's really can be a problem. But apparently the model can generalize it to the test set. So yeah.
Okay, thanks a lot.